In the previous video, we have seen how to obtain the volume of a solid if we know the cross-section of that solid by planes that are perpendicular to a certain axis. And we've seen some examples, but if you remember, finding this cross-section was not so easy. In this video, we are going to look at a particular case where finding the cross-section is easier. This is the case of solids of revolution. And what we mean by that is a solid that is generated by rotating a plane region about a line that is in that plane. Okay, maybe that's not quite clear, but if we look at an example, it should become obvious what it means. Let's say, for instance, you consider this plane region, so the area under the graph of the root function over the interval 0, 4, and you rotate it about a line in that plane. So for instance, you rotate it about the x-axis. Doing so, you see that what we obtain is a solid that now sits in a three-dimensional space instead of just the xy plane, and that looks like that. And you see that now our solid of revolution sits between the vertical plane x equals 0 and the vertical plane x equals 4. Using the technique of cross-section that we have seen in the previous section, what we would need to know is the cross-section by a plane x equals constant. So if you look at the case where x equals constant and look at the picture at the top, you have this red segment that corresponds to the part of the plane region that sits inside x equals constant, and we're going to rotate that around the x-axis. So we rotate this line segment around the x-axis, we obtain a disk as shown on the picture below. And all we need to know about a disk to know its area is its radius. And you see that the radius of the disk is really the length of that red segment, and that's just square root of x. In other words, the cross-section here is a disk of radius square root of x. Cross-section by a plane x equals constant, which if you look at the top picture would be a vertical plane that is perpendicular to the plane of the board. Of course, because it's perpendicular to the plane of the board, you wouldn't see it in the board. So that's why we have to tilt the picture in the picture below in order to see what's going on, and have this plane x equals constant, which is really perpendicular to the plane of the board for the first picture. Now in the second picture, it is tilted, and so we can see the cross-section. Now, if the cross-section is a disk of radius square root of x, the area of a disk is simply pi multiplied by the square of the radius of the disk. In other words, we get pi multiplied by root of x squared, in other words, pi x. And the formula we've established in the previous video is that the volume is then given by the integral of that area of the cross-section over the range of x values corresponding to the two bounding planes, two bounding vertical planes for the solid. In our case, x equals 0 and x equals 4. So we simply integrate pi x between 0 and 4. An antiderivative of x is x squared over 2. Pi is a multiplicative constant, I can pull it out. And when I evaluate x squared over 2 between 0 and 4, I get 8. And therefore, the volume is 8 pi. So as you can see, this is quite a bit easier than the exercise that we have seen on the wedge cutout of a cylinder. Now let's look at other examples. You may or may not know the formula for the volume of a solid sphere of radius r, say. So something like that, and we want to know the volume. So now, with our technique, we can establish this formula even if we don't know it. Because to obtain a solid sphere, what we can do is take a disk of radius r, so the bounding circle has equation x squared plus y squared equals r squared. For the picture here, r equals 3, but really we can do it with an arbitrary radius r. And then we rotate this solid disk about the x-axis, for instance. We could do it about the y-axis, but for us it's going to be easier in that case about the x-axis. And so rotating this disk about the x-axis, you can think of it as for each fixed x, you look at the part of this disk that sits above it and rotate it about the x-axis, and you obtain a disk. And this disk sits in the plane again x equal constant. It's a vertical plane that is perpendicular to the plane of the board, so we wouldn't see it unless we tilt it slightly, and that's why it doesn't look like a disk but more like an ellipse, because of the angle that the plane makes with the plane of the board. So all we need to know the area of the cross-section is the radius of this disk, and to obtain it, if you look at this right triangle, see that the hypotenuse is simply the radius of the bounding circle, so it's r. The base that sits along the x-axis has length x, because we are looking at the cross-section by the plane x equal constant. And therefore, this length, which is the radius that we're looking for, is square root of r squared minus x squared. In other words, we've established that the cross-section by x equal constant is a disk of radius square root of r squared minus x squared, where r is the radius of the sphere. So the cross-section has area pi multiplied by the square of the radius of a cross-sectional disk. So when I square a square root, the square root disappears, and what I obtain is pi multiplied by r squared minus x squared. According to the formula we've seen before, to obtain the volume of the solid of revolution, now all I need to know is integrate this area of the cross-section, in this case between negative r and r, on the picture between negative 3 and 3, but really between negative r and r. And so an antiderivative, to obtain an antiderivative I can pull out pi, because this is just a multiplicative constant. Antiderivative of r squared is simply r squared x, because r squared is really just a constant. And an antiderivative of x squared is x cubed over 3. We evaluate this function between negative r and r. And when we plug r, we get r cubed minus r cubed over 3. When we plug negative r, we get negative r cubed plus r cubed over 3. We take the difference of these two, and what we get is 4/3 of r cubed, and therefore the volume of a solid sphere of radius r is 4/3 pi r cubed.